So how did we get this periodic table, and why does it have that funky shape? Dmitry Mendeleev was a Russian scientist who first proposed the periodic law. And this law says that when the elements are arranged in order of increasing relative mass, certain sets of properties recur periodically. So you can imagine, I think this was back in like 1869, something like that. Many different elements had been discovered, random bits of information. There wasn't, a database or anything where all of this was organized. So he's looking at all the elements that were known, and he's trying to figure out some patterns, see if he can get more information out of it. I kind of imagine him listing the elements and some of their properties on index cards, and then just like rearranging them on the table and seeing what he can come up with. What he found is if he ordered them by increasing relative mass, they would fall into this order, and just like keys on a piano, certain properties would recur. So this one, helium, was a very inert gas. It doesn't react with anything. It's a gas at room temperature. And if you keep going over here, number 10 was also an inert gas at room temperature. And you went over here to number 18, and this is also an inert gas at room temperature. He noticed that lithium was a reactive metal, and sodium is a reactive metal, and potassium is a reactive metal. And so he saw these, just like this is the note C, and this is an octave higher and an octave higher. These properties recurred periodically. That's why it's called a periodic table. So he put them together so that elements with the similar properties were in columns, and the rows went by increasing relative mass. And that was the first periodic table. So we've since discovered more elements, and so here is an almost modern periodic table. We now have names for elements 113 through 118. It just came out last year. But we can get a lot of information just from the periodic table. So one thing we can tell is whether an element is a metal or a non-metal or a semi-metal. A semi-metal is also called a metalloid. It's like a humanoid robot is like a human, kind of shaped like a human, but it's not really a human. So a metalloid is like a metal, but not really. So on the periodic table, there's a stair-step line, starting here with boron and silicon, and it just goes like down the stairs here. That dividing line separates the metals from the nonmetals. In the upper right corner, all of these are nonmetal elements. In the lower left, these are the metals. There's a lot more metallic elements than nonmetals. And the ones right on the border here in the lavender are the metalloids. Kind of makes sense. Nonmetals, metals, and in between, those are things that kind of have in-between properties. The only one that's along that line that you need to know about that's not a semi-metal is aluminum. You probably have aluminum pans, aluminum cookie sheets at home, in your kitchen, aluminum silverware. We use aluminum. We recognize that aluminum is a metal. So aluminum is a metal, but pretty much everything else that touches this line, except for polonium, is a semi-metal. I don't care about polonium, so we're just going to ignore him. So metals, what are metals like? They're good conductors of heat and electricity. You can pound them into flat sheets. Malleability means the ability to pound something into a flat sheet. You can't do that with something like glass, right, or carbon. Other things, you pound them and they break, right? But a metal can be pounded into shape. It can be drawn into a wire. That's called ductility. Metals are often shiny. Lustrous is the fancy word for that. So those things are good to know. The most important thing here to know is that metals tend to lose electrons when they undergo chemical changes. And there's some examples. Nonmetals are in the upper right. Their properties are less consistent than the metals. Some are solids, some are gases. One of them's a liquid at room temperature. By the way, this periodic table over here on the wall, you'll notice that the elements symbols are in different colors. So if the symbol is in black, that means it's a solid at room temperature. If it's in red, it's a gas at room temperature. So you'll see that all those gases are nonmetals. There aren't any metallic gases at room temperature. And there are only two elements that are liquids at room temperature. One of them is mercury. Mercury is weird. It's a metal that's a liquid at room temperature. And bromine is a nonmetal that's a liquid at room temperature. The ones that are in white, they're just outlines, those are all man-made, and they are extremely unstable. So that's what the colors mean. So nonmetals tend to be poor conductors of heat and electricity, and they tend to gain electrons. So metals and nonmetals are kind of opposites of each other. Yeah, question?
Why do metals and nonmetals, what makes them tend to gain or lose electrons?
That's an excellent question. What makes nonmetals tend to gain electrons and metals tend to lose electrons? We're going to get into that probably more than you would like in another chapter. Pardon me?
Is it just the valence electrons, or are there other properties like the conductivity?
It has to do with the structure of the electrons, how the electrons are ordered. Yeah. So nonmetals tend to gain electrons, metals tend to lose them. And then the metalloids are in the middle. They have mixed properties. These are really useful in computers. They're called semiconductors because they have an intermediate electrical conductivity. They're not non-conductors, insulators, but they don't conduct like metals either. And what really makes them cool is you can influence their conductivity through changes in temperature, changes in pressure. You can change their conductivity and control it. And that is what has made so much of our wonderful technology possible. The cell phone in your pocket would not exist without semiconductors. So we should be able to find elements on the periodic table and identify metal, nonmetal, or metalloid. So S, nonmetal. That's sulfur. How about Cl? Nonmetal. That's chlorine. Ti. Yeah. Ti is a metal. How about Sb? It's right along that line. So it's a metalloid. Sb stands for antimony, and Ti is titanium. So you don't have to remember whether these things are metals or not. Some of them you do. Like, is iron a metal? Yeah, we know that. So, like, if you lose your mind on an exam, which happens, and you can't remember which side of the line the metals are on, well, you know iron's a metal, so which side of the line is iron on? Oh, okay, now I know. This side's the metals and the other's the nonmetals. So there are different sections in the periodic table. These first two columns, they're called groups or families. These first two columns and the last columns, the parts of the periodic table that stick up, those are called the main group elements. They have more predictable properties than the other elements. In the middle here is the block of transition elements. They're the transition from this cliff to that cliff. It's the transition. These guys are much less predictable. Their properties are just kind of all over the place. So the groups have numbers. This periodic table shows group 1A and group 2A. All of the transition elements have Bs. We don't even need to look at their numbers. The main group numbers are the ones we're interested in. Group 3A, 4A, 5A, 6A, 7A, 8A. You'll also see them just numbered 1, 2, and then they'll keep going across the transitions, and they'll come over here, and this will be 13, 14, 15, 16, 17, and 18. So that's the official IUPAC numbering system. The one with the letters in it is the current U.S. usage. Since we're currently in the U.S., I say we use that one. I think it gives more information. But notice there is a common theme here. If you just knock the 10 off, 16 and 6, 17 and 7, those numbers are going to be useful to us in predicting some things. The rows in the periodic table are called periods, and those are also numbered, 1, 2, 3, 4, 5, 6, 7. So this element, Ga, that's gallium, is in period 4. It's in group 3A or group 13, just different names for the same group. Some of these columns, which are called groups or families, have special names. So because of how Mendeleev arranged the elements within a column or group have similar properties. And that's why we call them families. Because many times members of a same family have some similar characteristics, right? You all know some people who, you know them and then you meet their brother and you're like, oh yeah, that's your brother, right? You can just tell, right? There's a family resemblance. So that's true with the elements too. So some of these groups have special names and we need to know what they are. So group 1A, these are called the alkali metals. Now, is hydrogen a metal? No. We look at this periodic table, we see that hydrogen is a gas at room temperature. What the heck is he doing over there with the metals? Hydrogen I view as the baby brother of the element family. And what does that youngest child, you know how that works. The youngest child gets away with all kinds of stuff that the older one would have been just had the crap beat out of him for, right? And you just laugh, oh yeah, he's so cute, right? That's what hydrogen is. He breaks all the rules. He's going to be an exception to almost anything. So he's not a metal, but on the periodic table he hangs over here with the metals. So he's not technically part of that group. Next to that group we have the alkaline earth metals. I don't know what's going on with my pointer. Having Wi-Fi issues. Group 2A, these are called the alkaline earth metals, so all of these guys. And then group 7A has a name, these are the halogens, and group 8A has a name, those are the noble gases. So if I asked you, what is the noble gas in period 2? You should be able to tell me that. So these are the noble gases. The first row, this is period 1, this is period 2. So the noble gas in period 2 is neon. The other groups don't have special names. These guys down here, we're not going to do much with them, but I would like to explain why they're stuck down here. If you look at the numbers, 56, 57, and then it jumps to 72. What is up with that? Well, we really should take a pair of scissors and cut the periodic table and spread it apart. If you look at the one that we have in lab, we actually did that. We used a pair of scissors and we cut it up because to fit it above the whiteboard, it doesn't fit this way. So you cut it and you stick this guy in here. So 57, from here you jump down here, 58, and then it goes in order to 71, and then it goes back up here. So these guys are called the lanthanides because they come after lanthanum. And in this bottom period, this is actinium, and so the elements that come after actinium are called the actinides. Why do we pull these out? Because on a regular piece of paper, the periodic table wouldn't fit very well. It'd be just, the aspect ratio would be all off. Okay? Nothing fancier than that. I'm going to go over this part pretty quickly. Alkali metals are very reactive. Sodium will generate hydrogen gas in so much heat that it will explode if you put it in water. Crazy reactive, just super reactive. Alkaline earth metals, not as reactive, but still quite reactive. These are metals that will burn and react with water. You put calcium metal in water, and it undergoes a reaction, a very rapid reaction. Very active metals. Over in group 7A, the halogens, these are reactive nonmetals. Some of them are gases. Bromine's a liquid, iodine is a solid at room temperature. And then next to them are the noble gases. They're very chemically inert. A neon sign contains neon. Helium balloons have helium. These just make very few compounds. So, To which group or family of elements does each element belong? So they're all going to have a group number. Some of them will have names. Li. It's an alkali metal, so it's in group 1A, or the other numbering system is 1. And it's got a family name, the alkali metals. How about B? So it's in group 3A, or group 13. That group doesn't have a special name. How about I? Yeah, it's over in group 7A or 17, and that family is called the halogens. How do you know it's the halogens? You memorize it. More stuff for your flashcards. Argon, Ar, noble gas. So that's, the group number is 8A or 18, and the name is noble gases. Any questions? Yeah.
Are you going to use the number or are you going to use
I will mostly use the number that has the A, because I think it's more useful. I do try to put both of them on here because some periodic tables don't have the group numbers with the A's. This periodic table, as we purchased it, just had them numbered 1 through 18. But they provide stickers in case you want to put the other numbers up there. And so that's why there's little stickers. Those are with Roman numerals. And the group 7A sticker is missing, but I think we can deal with that. So why do we need names of some of those groups? Because it's easier to say, oh, well, the halogens do this. They have common features, common characteristics, and so we'll sometimes talk about them as a group. And so when I say halogens, you need to know that those are fluorine, chlorine, bromine, iodine in group 17 or 7A.